NASA pointed some of the most advanced eyes in the solar system at ThreeI Atlas, and those eyes went blind. The Mars Reconnaissance Orbiter's newly upgraded sensors should have produced crystal-sharp detail, yet all they returned was a glowing smear. But down here on Earth, Sarah from Nebraska, armed with a $400 telescope and a backyard lawn chair, captured crisp geometric jets and a strange ring curling around the object like a whisper of structure. That mismatch isn't an accident. It's the signature of what physicists call a visibility paradox, a moment when cutting-edge instruments lose clarity, while simpler optics see straight through the chaos. Tonight, we dive into the theory that ThreeI Atlas is wrapped in a high-energy plasma shield, capable of scrambling billion-dollar sensors while letting amateur gear slip under the radar. And with a powerful solar storm only 72 hours away, that shield may be on the brink of collapse. If it does, the universe might reveal something ordinary, or something far less comforting. Either way, what comes next could rewrite everything we thought we knew about this interstellar visitor. If this mystery continues to keep you awake the way it keeps me awake, hit subscribe so you're here when the next piece of this puzzle emerges. Tell me in the comments where you're listening from, what hour it is in your corner of the world, and your thoughts on this alleged plasma shield. Part 1. The Paradox Revealed. Picture this. On November 19th, 2025, NASA's Mars Reconnaissance Orbiter swivels its billion-dollar high-rise camera away from the red planet's surface and aims outward into the black. The target? ThreeI Atlas, the third confirmed interstellar object ever detected, a visitor from another star system streaking through our cosmic neighbourhood at velocities that defy solar origin. Engineers hold their breath. This is the moment, the closest high-resolution imagery we'll ever capture of something born in alien darkness, something that's travelled for millions of years just to grace us with its presence for a few fleeting months. The shutter clicks. Data streams back across 30 million kilometres of emptiness. Scientists crowd around monitors in Pasadena, in Houston, at the European Space Agency. They're expecting revelation. Instead, they get a fuzzy, pixelated smudge. A glowing blob, featureless, amorphous, like someone smeared Vaseline across the lens of humanity's most advanced orbital camera. At 30 kilometres per pixel, ThreeI Atlas appears as nothing more than a white stain against the cosmic canvas. No jets, no structure, no geometric precision, just blur. Now freeze that image in your mind and pivot your attention earthward. Down here, in suburban backyards from Arizona to Australia, amateur astronomers are posting images to forums and Reddit threads that tell a wildly different story. Their equipment? Consumer-grade telescopes you could buy online for less than the cost of a used car. Their processing power? Laptops running free stacking software. And yet, in their images, ThreeI Atlas reveals itself. Sharp, geometric jets emanate from what appears to be a central nucleus. Ring-like structures encircle the object. Multiple tails fan outward in configurations that shouldn't exist according to standard comet physics. These aren't peer-reviewed findings, mind you. They're not in Nature or the Astrophysical Journal. They're screenshots posted at 3 in the morning by people with day jobs, accompanied by comments like, "Anyone else seeing this?" and "NASA, you seeing what I'm seeing?" How is this possible? How can state-of-the-art spacecraft instruments, designed by teams of PhD engineers and calibrated to detect the faintest whispers of light across interplanetary distances, see less than a hobbyist with a Dobsonian reflector and a decent CCD sensor? This isn't a question of image processing or enthusiastic overinterpretation. We're talking about a fundamental discrepancy in observed structure. The amateurs claim to see geometry. NASA sees fog. Welcome to what I'm calling the visibility paradox. It's the idea that our highest-end sensors are somehow failing to detect structures that lower-cost, ground-based instruments appear to reveal with startling clarity. And if that sounds trivial to you, consider what it implies. Either we're facing a catastrophic misunderstanding of how our observational tools work, or something about ThreeI Atlas itself is actively preventing our best equipment from seeing it clearly. Those are the only two options on the table, and neither one is comforting. The stakes here aren't academic. We're dealing with only the third confirmed interstellar object in human history. Before 2017, we'd never seen one. Then came 1I/Oumuamua, that cigar-shaped enigma that accelerated away from the sun in ways we still can't fully explain. 2 years later, 2I/Borisov showed up, more comet-like, more familiar, but still a stranger bearing chemical signatures from another stellar nursery. Now, 3I Atlas arrives, and it's weirder than both predecessors combined. Higher carbon dioxide ratios than any solar system comet. Polarization signatures unlike anything in our databases. Non-gravitational acceleration that defies easy explanation, and now, apparently, the ability to hide in plain sight. The conventional explanation goes like this. Observing an interstellar object is hard. Really hard. These things move fast, they're small, they're faint, and they're wrapped in expanding clouds of gas and dust that obscure the nucleus. Distance and angular resolution conspire against us. HiRISE, for all its power, was imaging 3I Atlas from roughly 30 million kilometres away, about a fifth of an astronomical unit. At that range, even a 10-kilometre nucleus would appear as just a handful of pixels. Add the coma, add the motion blur, add the signal-to-noise challenges, and blur is exactly what you'd expect. Mystery solved, right? Except the amateur community isn't buying it. They've been tracking this object for weeks, using different filters, different exposure times, different stacking methods. Some claim they're seeing structures that persist across multiple nights, structures that move and evolve in ways consistent with active jets venting material into space. Are they all suffering from pareidolia? Are they seeing patterns in noise, faces and clouds? Maybe, probably even. But the consistency of their reports is unnerving. When a dozen independent observers scattered across 3 continents all sketch the same basic geometry, you start to wonder. So here's the question that should keep you awake tonight. What if the issue isn't incompetence? What if NASA's cameras aren't broken and the amateurs aren't hallucinating? What if the problem is physics we don't fully account for? What if 3I Atlas is surrounded by something, an environment, a field, a cloud of charged particles that interacts with electromagnetic radiation in ways that scramble high-tech sensors while allowing lower frequency, longer exposure observations to punch through? What if, in other words, the object is hiding itself, not through intent necessarily, but through the sheer exotic nature of its physical state? That's the rabbit hole we're about to descend. In the next few minutes, we'll examine exactly what NASA's imagery does show and, more importantly, what it doesn't. We'll explore the gap between official data releases and grassroots observations. We'll investigate a hypothesis that sounds like science fiction, but might be grounded in plasma physics. That 3I Atlas is wrapped in a high-energy electromagnetic shield that actively scatters and absorbs the very light we're trying to use to see it. And we'll ask whether a massive solar storm, predicted to slam into the inner solar system around November 22nd, might strip that shield away and finally reveal what's been hiding underneath all along. This is not a conspiracy theory. This is an investigation into the limits of perception, the boundaries of our instruments, and the possibility that the universe still holds surprises our technology wasn't designed to comprehend. The visitors from other stars may not look like what we expect. They may not behave like what we expect, and they may not be visible in the ways we expect. So buckle in. Because what we're about to explore is the possibility that we've been looking at 3I Atlas all along, but we haven't been seeing it. Part 2. Latest developments. NASA's imagery drop and public response. The image drops on November 19th, 2025, and within hours the internet fractures into a dozen competing narratives. NASA's press release is cautious, measured, diplomatic. The HiRISE camera aboard the Mars Reconnaissance Orbiter successfully captured 3I Atlas during its closest approach to Mars, obtaining what they describe as valuable in situ observations of an interstellar object from an unprecedented vantage point. The phrase unprecedented vantage point does heavy lifting there. What they're not saying, what they're carefully dancing around, is that the image itself is profoundly underwhelming. At approximately 30 kilometers per pixel, the object appears as a diffuse white blob, roughly 10 pixels across. No nucleus visible, no jets resolved, no surface features, just a Gaussian smear of reflected sunlight bleeding into the black. But HiRISE wasn't operating alone. NASA marshals additional data to pad the release. The MAVEN spacecraft, also orbiting Mars, contributed ultraviolet imagery showing a hydrogen envelope around the object, evidence of water vapor breaking down in sunlight, exactly what you'd expect from a comet shedding its icy skin as it approaches perihelion. Down on the Martian surface, The Perseverance rover pointed its cameras skyward during the object's transit and captured a faint streak against the starfield. These are presented as complementary data points, pieces of a mosaic that, assembled together, paint a picture of scientific success. Look at all the assets we deployed, the release seems to say. Look at this coordinated effort. Appreciate the logistics of pointing multiple spacecraft at a moving target, millions of miles away. The public response is immediate and bifurcated. On one side, the science enthusiasts and space agency faithful celebrate the achievement. This is the first time multiple Mars-orbiting instruments have simultaneously observed an interstellar object. The data, limited though it may be, represents real engineering triumph. The fact that HiRISE could even locate and track something as small and fast as ThreeI Atlas from Mars orbit is genuinely impressive. These people see the glass as half full. They understand that observational astronomy is a game of incremental gains, that every data point matters, that even blurry images contain information about albedo, coma extent, and activity levels. On the other side, frustration bordering on anger. Social media erupts with accusations of withholding data, of soft launching disappointing results to manage expectations, of NASA playing public relations games instead of releasing the raw, unprocessed files for independent analysis. The amateur astronomy community, already buzzing with their own observations, feels vindicated and dismissed simultaneously. They've been posting detailed images, or what they claim are detailed images, for weeks. Some show distinct jets, others capture what looks like a ring or shell structure surrounding a bright central point. A few even suggest non-radial symmetry, features that rotate or pulse over timescales of hours. None of this appears in NASA's release. Where's the structure? Where are the jets? Why does the most expensive camera system ever launched see less than a 12-inch Newtonian reflector operated by an insurance adjuster in Colorado? The formal scientific press tries to walk a middle path. Articles emphasize the technical challenges, the speed of the object, the distance, the angular resolution limits, the difficulty of pointing instruments designed to study planetary surfaces at a moving target in deep space. These are all real constraints. HiRISE's primary mission is mapping Mars at resolutions fine enough to spot individual boulders and layered sediments. Repurposing it to image a comet 30 million kilometers away is like using a microscope to photograph a bird in flight. You might get lucky, but you're working outside the instrument's design parameters. What emerges from this cacophony is a tension that cuts to the core of modern astronomy, the mismatch between expectation and capability. We live in an era where the James Webb Space Telescope can image galaxies forming 13 billion years ago, where Event Horizon Telescope arrays can photograph the shadow of a black hole 55 million light-years distant. Our instruments have achieved the miraculous so often that we've recalibrated our sense of the possible. So when NASA points its Mars-orbiting camera at an object a mere 30 million kilometers away and gets a blurry blob, it feels like failure. It feels like something went wrong. But here's where the visibility paradox sharpens into focus. Distance and resolution don't explain why ground-based observers, working with far inferior equipment, claim to see structure. Yes, they're using different techniques, long exposures, image stacking, software-based noise reduction. Yes, they're integrating light over much longer time periods, which can reveal faint features that brief exposures miss. But they're also shooting through Earth's atmosphere, dealing with light pollution, fighting turbulence and scintillation. Every advantage they have in terms of integration time is offset by disadvantages in observing conditions, and yet, persistently, they report seeing things. The disconnect breeds speculation. Some suggest NASA is downplaying anomalies to avoid panic or premature conclusions. Others propose that the agency's data pipelines, designed for planetary geology, not cometary science, might be inadvertently suppressing real signals that fall outside expected parameters. A smaller but vocal minority whispers about deliberate obfuscation, though their motivations for such a conspiracy remain murky. Why would NASA hide details about a comet? What's the threat model? The more prosaic explanation, the one that neither side wants to fully embrace, is that we're looking at a genuine unknown. Maybe ThreeI Atlas possesses physical characteristics that make it difficult to observe with certain types of instruments or from certain angles. Maybe its coma is optically thick in some wavelengths and transparent in others. Maybe the plasma environment around the object, ionized gas and dust, charged particles spiraling in magnetic fields, scatters light in ways that degrade high-resolution imagery while allowing lower-resolution observations to integrate enough photons over time to reveal structure. Maybe, in other words, the blur isn't a failure of our tools, it's a property of the object itself. This idea that ThreeI Atlas might be surrounded by an environment that actively interferes with observation is not something NASA's press release entertains. It's too speculative, too far outside the comfort zone of peer-reviewed planetary science. But it's sitting there in the data, or rather in the absence of data, like a shadow cast by something we can't quite see. The amateur images, dismissed by some as artifacts and noise, might be telling us something profoundly important, that the object doesn't want to be seen clearly, not because it's conscious or deliberate, but because its physical state, its composition, its electromagnetic environment, its interaction with the solar wind creates conditions that obscure it from certain observers while revealing it to others. So we're left with a mystery wrapped in a blur. NASA has given us the official story: distant, small, faint, challenging to observe, mission accomplished despite limitations. The amateurs have given us the underground narrative: structure, jets, geometry. Something weird is happening, and why won't anyone acknowledge it? And between these two poles lies a question that neither side is quite asking yet. What if both are right? What if NASA genuinely saw a featureless blob, and the amateurs genuinely saw jets and rings, and both observations are accurate snapshots of an object that appears radically different depending on how and when you look at it? What if the problem isn't the hardware at all, but what the object does to the hardware? Part 3. Introducing the plasma shield hypothesis. Let's put a name to the thing that might be hiding ThreeI Atlas from our best cameras. Let's call it the plasma shield hypothesis. It sounds like something out of Star Trek, and maybe that's why no one in the official channels wants to say it out loud. But strip away the science fiction associations and what you're left with is a straightforward, if exotic, physical possibility. That ThreeI Atlas is surrounded by a region of high-energy plasma dense enough and active enough to scatter, absorb and refract electromagnetic radiation in ways that fundamentally alter what we can see. First, let's define terms. Plasma, in the astrophysical sense, is matter in its fourth state, beyond solid, liquid and gas. It's what you get when you heat gas to the point where electrons are ripped away from their atomic nuclei, creating a soup of charged particles, free electrons zipping around, positive ions drifting, all of them responding to electric and magnetic fields. Plasma conducts electricity, it generates its own magnetic fields, and it interacts with light in complex, sometimes counterintuitive ways. The sun's corona is plasma. The tail of a comet lit by solar wind is plasma. The auroras dancing above Earth's poles are plasma. It's everywhere in space, and it doesn't behave like ordinary matter. Now imagine a comet nucleus. ThreeI/Atlas's presumed solid core of ice and rock and organic compounds, outgassing furiously as it plunges toward the inner solar system. Water vapor, carbon dioxide, carbon monoxide, trace organics, all boiling off the sun-heated surface and expanding into the vacuum. Some of that gas gets ionized by solar ultraviolet radiation, and the solar wind itself turning into plasma. Normally this plasma forms the classic ion tail, a blue streak pointing away from the sun, driven outward by the solar magnetic field. It's beautiful. It's well understood. It's in every textbook. But what if ThreeI Atlas is generating plasma in quantities or configurations that go beyond the textbook model? What if its composition, that bizarre carbon dioxide to water ratio we'll explore later, creates unusually dense ionization? What if the magnetic field embedded in the solar wind interacts with the object in a way that traps or compresses plasma around the nucleus instead of blowing it cleanly away? What if you end up with a shell or halo of charged particles co-moving with the comet, forming a kind of electromagnetic fog that surrounds the object like an atmosphere? This is the plasma shield hypothesis. It's the idea that ThreeI Atlas has somehow generated or accumulated a region of dense plasma that functions, intentionally or not, as a cloak. And here's why that matters for visibility. Plasma scatters light. The free electrons in plasma can absorb and re-emit photons, blurring images. The refractive index of plasma varies with electron density and frequency, which means light passing through it bends and disperses like light through water, but in ways that depend on wavelength. Ultraviolet light might be absorbed entirely. Visible light might scatter into a diffuse glow. Infrared could punch through relatively cleanly, or it might be blocked by dust grains mixed into the plasma. The point is, you don't get a clear, unobstructed view. You get distortion. Think of it like looking at something underwater from above the surface. The object is there, but refraction bends the light, making it appear shifted or blurred. Or think of heat shimmer above a highway on a summer day. The hot air creates refractive index variations that make distant objects waver and dance. Now scale that up to space. Replace hot air with ionized gas at thousands of degrees. Add magnetic fields that can twist and channel the plasma, and you start to see how an object could be physically present, but optically obscured. This is why the amateur observations become crucial. If they're using longer integration times, stacking dozens or hundreds of images, they might be averaging through some of the plasma-induced noise. If they're observing in slightly different wavelengths, maybe red filters that penetrate better than blue, they might be catching glimpses of structure that shorter wavelength, high-resolution instruments miss. HiRISE, optimized for crisp visible light imaging of Martian geology, might be the worst possible tool for seeing through a plasma veil. It's designed for clarity, not for integrating faint signals over time. It's a sprinter, not a marathon runner. The hypothesis also offers an explanation for another puzzling aspect of ThreeI Atlas, its variability. Multiple observers have reported brightness fluctuations, changes in tail morphology, and apparent shifts in activity level over timescales of days or even hours. If the plasma environment is dynamic, responding to changes in solar wind pressure, outgassing rates, or the comet's own rotation, then what we see would change depending on when we look. Maybe HiRISE caught the object during a moment when the plasma shield was at maximum density, rendering the nucleus completely invisible. Maybe the amateurs, observing hours or days earlier, caught it during a lull when the shield thinned enough to reveal jets. Of course, this is speculative. Wildly speculative. No peer-reviewed paper has proposed a plasma shield around ThreeI Atlas. No spectroscopic analysis has definitively detected the kind of extreme ionization this would require. We're extrapolating from fragmentary evidence, the blurry NASA images, the contradictory amateur reports, the general weirdness of the object's behavior. But speculation is how science advances. You notice something that doesn't fit, you propose a mechanism, and then you test it. And the beauty of the plasma shield hypothesis is that it's testable. If it's real, there should be signatures we can look for. For example, plasma emits light at specific wavelengths corresponding to the elements being ionized. Oxygen plasma glows green. Hydrogen glows red. If ThreeI Atlas has a dense plasma shell, spectroscopy should reveal bright emission lines. Radio observations should show unusual dispersion or scattering. Ultraviolet imaging should see strong signals from the ionization zone. The fact that we haven't seen overwhelming evidence for any of this yet is a mark against the hypothesis. But absence of evidence isn't evidence of absence, especially when we've barely started looking with the right tools. There's another angle here, one that edges closer to the truly strange. What if the plasma shield isn't a passive byproduct of normal outgassing, but something more organized? What if the magnetic field structure around ThreeI Atlas is unusually strong or geometrically peculiar, creating stable plasma configurations that wouldn't normally occur? We know that magnetic fields can bottle plasma. The Earth's magnetosphere does exactly this, trapping charged particles in radiation belts. Could a comet generate its own mini-magnetosphere? Could interactions between the solar wind and an intrinsic magnetic field create a stable shell? Now we're venturing into territory where natural explanations start to blur with more exotic possibilities. A self-organized plasma shield sounds almost deliberate. It sounds engineered. And that's where the conversation gets uncomfortable, because once you start asking whether ThreeI Atlas might be generating an electromagnetic cloak, whether by accident of chemistry and physics or by design, you're one step away from asking whether it's artificial. We'll get to that minefield later. For now, let's just acknowledge that the plasma shield hypothesis opens doors we're not used to walking through. If this hypothesis is true, even in its mildest form, then we're not simply looking at a blurry comet. We're looking at an entity that is hidden, cloaked by its own electromagnetic envelope. The blur isn't a failure, it's a feature. And the question becomes, what's underneath? What are we not seeing? And most urgently, is there any way to strip the veil away and finally get a clear look at what's been travelling across light years to visit us? Part 4. Why the timing matters. Solar storm incoming. Here's where the story takes a turn from academic mystery to time-sensitive thriller. As 3I Atlas cruises through the inner solar system, wrapped in its hypothetical plasma, shroud, the sun is preparing to throw a punch. Solar weather forecasters, yes, that's a real job, are tracking a significant solar storm predicted to impact Earth and the inner planets around November the 22nd, 2025. We're talking about coronal mass ejection, or CME, a billion-ton bubble of magnetized plasma hurled outward from the sun's corona at speeds approaching 1,000 kilometers per second. When that wave of charged particles slams into the inner solar system, everything changes. Solar storms are common enough. The sun goes through 11-year cycles of activity, and during solar maximum, CMEs happen almost daily. Most are weak, barely noticeable except to sensitive magnetometers. But every so often, the sun uncorks something powerful, a fast CME with a strong embedded magnetic field, travelling directly toward Earth. When those hit, satellites glitch, power grids strain, auroras blaze as far south as the Caribbean. They're beautiful and dangerous in equal measure. For a comet, a solar storm is even more dramatic. Remember that a comet's ion tail is shaped by the solar wind, the constant stream of charged particles flowing outward from the sun. A CME is like turning that stream into a fire hose. The sudden increase in solar wind pressure compresses the comet's magnetosphere, if it has one, and blows the ion tail into new configurations. Some comets brighten suddenly during solar storms as increased ionization pumps more energy into the coma. Others seem to dim as material is stripped away faster than it can be replenished. The plasma environment around the comet becomes turbulent, chaotic, unpredictable. Now apply this to the plasma shield hypothesis. If 3I Atlas is surrounded by a dense, stable plasma shell, that shell is being held in place by a delicate balance of forces, outgassing pressure from below, solar wind pressure from outside, magnetic field tensions weaving through the charged particles. It's a dynamic equilibrium, constantly adjusting but roughly stable over hours or days. A solar storm disrupts that balance. The sudden spike in solar wind pressure could compress the shield, making it denser and even more opaque, or it could shred the shield entirely, blowing it away like fog before a gale, and finally exposing the nucleus beneath. This is why the timing matters. If the solar storm hits as predicted, and if the plasma shield hypothesis has any validity, then the next few days could provide the critical test. Observers around the world, professional and amateur, will be watching 3I Atlas as the CME arrives. If the object suddenly brightens, or if previously hidden jets become visible, or if its coma morphology shifts dramatically, that's strong evidence for a plasma-mediated visibility effect. The storm would be stripping away the cloak. There's precedent for this. Comets have been known to undergo sudden outbursts during solar activity. Comet 17P/Holmes famously brightened by a factor of nearly 1 million in just 42 hours back in 2007, possibly triggered by some internal event but likely amplified by solar wind conditions. Comet 73P/Schwarzmann-Wachmann. One is famous for irregular, explosive brightenings. We don't always understand the mechanisms, but the correlation with solar activity is suggestive. If 3I Atlas behaves anomalously around November 22nd, we'll have our answer, or at least a very strong hint. But there's a darker possibility here, one that should give us pause. What if the solar storm doesn't reveal structure, but instead generates false structure? Plasma is dynamic and unpredictable. A CME impact could create transient features in the coma, loops of magnetic field, filaments of compressed plasma, spirals of dust caught in turbulent eddies that mimic jets or shells but aren't actually connected to the nucleus. We could be fooled into thinking we're seeing the real object when we're actually seeing storm-generated artifacts. Distinguishing genuine structural features from transient plasma phenomena requires careful spectroscopy and time-resolved imaging. It requires patience. And right now, with the clock ticking down to storm impact, patience is in short supply. There's also the question of what this means for the object's trajectory and behaviour. non-gravitational forces, the rocket effect from outgassing, already perturb ThreeI Atlas's orbit. If a solar storm dramatically changes the outgassing rate or the plasma environment, those forces could spike temporarily. The object might accelerate unexpectedly, or its spin state could change. These are measurable effects, and if observed, they'd provide indirect evidence for a dense plasma environment responding violently to external forcing. So we're in a waiting game. Professional observatories are scheduling time on their instruments. Amateur networks are coordinating observing runs. Space-based assets, SOHO, Stereo, the Solar Dynamics Observatory, are tracking the CME as it propagates outward. Everyone wants to see what happens when the storm hits. Will the veil lift? Will we finally get a clear view of this interstellar visitor? Or will the storm just add more confusion, more noise, more ambiguity to an already murky picture? This is the moment. This weekend, possibly within the next 72 hours, we might witness the reveal. If ThreeI Atlas is hiding behind plasma, the solar storm could strip that shield away like wind-tearing fog from a mountain peak. What's underneath might be mundane. An ordinary comet nucleus venting gas and dust in predictable patterns. Or it might be extraordinary. Geometric jets that don't fit our models, surface features that suggest unusual composition, activity patterns that imply something other than passive ice sublimation. We won't know until we look, and we can't look clearly until the shield, if there is a shield, comes down, and if nothing changes, if ThreeI Atlas weathers the solar storm without any dramatic shift in appearance or behaviour, then the plasma shield hypothesis takes a hit. Not a fatal blow, perhaps. There are ways to salvage it, to argue that the shield is more robust than expected, but a hit nonetheless. Science progresses through failed predictions as much as confirmed ones. If we predict a reveal, and it doesn't happen, we learn something important about the limits of plasma-mediated obscuration. Either way, the next few days are critical. The solar storm is coming, the object is in our crosshairs, and for the first time since ThreeI Atlas entered our detection range, we have a chance to see it without the fog. All we can do now is watch, and wait, and hope that when the storm passes, the picture becomes clearer rather than more confused. Because right now, we're navigating by instruments that might not be showing us the truth, and that should terrify anyone who cares about knowing what's really out there in the dark. Part 5. Roadmap for the video. Let's take a breath and survey the terrain we've covered and the ground still ahead. So far, we've established the visibility paradox. Billion-dollar sensors seeing less than backyard telescopes. We've examined NASA's November 19th imagery release and the bifurcated public response. Celebration from some, frustration from others. We've introduced the plasma shield hypothesis as a possible physical explanation for why ThreeI Atlas appears blurry to high-tech instruments, but potentially structured to long-exposure amateur observations. And we've discussed the timing the solar storm predicted for November 22nd that might serve as a natural experiment, stripping away the hypothetical shield and revealing what's beneath. That's Act 1. The setup, the mystery, the core claim. We've baited the hook. Now we need to explore the depths. And that means diving into evidence that goes beyond simple visibility issues. Because ThreeI Atlas isn't just optically anomalous, it's anomalous in nearly every measurable way. Its motion defies easy explanation. Its composition is unlike anything in our solar system. Its polarization signature is unprecedented, and when you stack these anomalies together, the visibility paradox stops looking like an isolated quirk and starts looking like one symptom of something much larger and stranger. Act 2, which we're about to enter, will take us through the technical weirdness in detail. We'll examine the non-gravitational acceleration, the fact that ThreeI Atlas is deviating from a purely gravitational trajectory more than it should, given its observed size and activity level. We'll crunch some numbers, look at momentum budgets, and ask whether standard cometary outgassing can really explain the forces at play. We'll explore polarimetry data showing that deep, narrow negative polarization branch that's never been seen in comets or asteroids before, and what that implies about surface composition and particle structure. We'll dive into spectroscopy from the James Webb Space Telescope, revealing a carbon dioxide to water ratio so extreme it places ThreeI Atlas 6 standard deviations outside the normal distribution for solar system comets. We'll ask what that means for origin, for processing history, for the possibility that this object spent billions of years being bombarded by cosmic rays in interstellar space. And then we'll pivot to the truly speculative territory, alternative theories that go beyond natural explanations. We'll confront the elephant in the room, the artificial origin hypothesis, championed by scientists like Avi Loeb and dismissed by others as premature sensationalism. We'll examine the arguments on both sides fairly, without tipping the scales toward belief or dismissal. We'll explore how the plasma shield hypothesis, if true, could be either a natural consequence of exotic chemistry and solar-wind interaction, or, and this is where it gets weird, a deliberate feature, a cloak. And we'll ask the uncomfortable question: if you wanted to disguise something artificial as natural, how would you do it? Spoiler: you'd probably wrap it in a comet-like envelope and let it coast through the solar system looking mostly normal, save for a few anomalies that could be explained away by reference to its interstellar origin. Act 2 will also include a deeper technical discussion of how plasma obscures light, how different sensors at different wavelengths and integration times might see radically different things, and why the visibility mechanisms we're invoking aren't just hand-waving, but grounded in real plasma physics. We'll explore the challenges to the plasma shield hypothesis. Where's the energy coming from to sustain such a structure? Why don't we see overwhelming spectroscopic evidence of ionization? How do we reconcile the shield concept with the radio emissions recently detected from ThreeI Atlas? These are hard questions, and we won't shy away from them. Act 3, the final act, will zoom out. We'll place ThreeI Atlas in the broader context of interstellar object science, comparing it to 1I/Oumuamua and 2I/Borisov, and asking what these three visitors tell us about the galaxy's population of rogue objects. We'll discuss the future of interstellar object observation, missions like ESA's Comet Interceptor, improvements in detection networks, the role of AI, and machine learning in processing faint signals. We'll examine related news: China's Tianwen-1 mission contributing imagery, the geopolitics of who gets to observe what and when, the tension between open science and national prestige. We'll also explore space weather more broadly, because the solar storm isn't just relevant to ThreeI Atlas. It's a reminder that the environment between the planets is active and dynamic, that our observations are always mediated by the medium through which light travels. We'll talk about how solar storms affect not just comets, but spacecraft, communication networks, even Earth's power infrastructure. The cosmic and the terrestrial are linked in ways we often forget. And finally, we'll reflect on epistemology, the nature of knowing and seeing. We'll ask how much of science is limited not by the phenomena themselves, but by the tools and frameworks we use to observe them. We'll consider the role of amateur astronomers in pushing boundaries and questioning official narratives, and whether the democratization of observational astronomy via cheap CCD cameras and open-source software is changing the game. We'll think about data transparency, about the pressure on space agencies to release raw data versus processed products, about how AI pipelines might inadvertently filter out anomalies that don't fit expected patterns. By the end, you'll have a comprehensive understanding of not just ThreeI Atlas, but the process of scientific investigation itself, the tension between caution and curiosity, between skepticism and openness to the unexpected. You'll see how a single, fuzzy image can cascade into a sprawling investigation touching on plasma physics, cometary science, interstellar astronomy, space weather, geopolitics, and the philosophy of observation. You'll understand why the visibility paradox matters, whether or not the plasma shield hypothesis pans out. Most importantly, you'll be equipped to watch the next days and weeks with informed eyes. When the solar storm hits, when new observations are released, when amateur forums light up with claims of jets or rings or brightness spikes, you'll know how to evaluate those claims. You'll understand the difference between wishful thinking and genuine anomaly, between noise and signal, between the mundane and the truly strange. You'll be able to navigate the conversation without getting lost in hype or drowning in technical jargon. This is a story about an object from another star, yes, but it's also a story about us, about how we look at the universe, what we expect to find, and what we do when reality refuses to cooperate with our expectations. ThreeI Atlas might be just a comet, weird but ultimately natural, or it might be something else, something that forces us to expand our categories and rethink our assumptions. We won't know until we look more carefully, with better tools, at better times, from better angles. And maybe, just maybe, we'll need to admit that seeing isn't as simple as pointing a camera and pressing a button. Maybe the universe has blind spots built in, and learning to see past them is the real challenge. Part 6. Anomalies in detail, acceleration, mass, and mathematics. Let's get technical. Let's talk numbers, because numbers don't lie, they just sometimes refuse to add up the way we expect. 3I Atlas is not behaving like a typical comet, and the first major red flag shows up in its motion. Astronomers tracking the object have detected what's called non-gravitational acceleration. The comet is deviating from the path it should follow if gravity alone were steering it. This isn't unusual in itself. Most active comets exhibit non-gravitational acceleration because they're constantly venting gas and dust. Every molecule that escapes the nucleus carries momentum, and by Newton's third law, the nucleus recoils in the opposite direction. It's the rocket effect, and it's been understood since the 1800s. But here's the problem. The amount of acceleration we're seeing doesn't quite match the amount of outgassing we're observing. To generate the observed trajectory deviation, 3I Atlas would need to be venting material at rates that seem high, not impossibly high, but uncomfortably high, given its estimated size and activity level. The math gets messy fast, so let me walk you through the basics. When you measure a comet's position over time and compare it to predictions based solely on gravitational forces from the Sun, planets, and other bodies, you often find small discrepancies. Those discrepancies can be modelled as extra accelerations, typically broken into radial components pointing toward or away from the Sun, and transverse components perpendicular to the Sun-comet line. For 3I Atlas, the radial acceleration is positive, meaning it's being pushed away from the Sun harder than expected. That's consistent with outgassing on the sunward side, jets of vapour and dust blasting into space, pushing the nucleus backward. To calculate how much mass needs to be lost per second to produce a given acceleration, you use basic momentum conservation. Force equals mass flow rate times exhaust velocity. Solve for mass flow rate, and you get an estimate of how much gas and dust the comet must be shedding every second to explain the trajectory shift. Studies of 3I Atlas place the dust production rate at around 180 kilograms per second, at 2 astronomical units from the Sun. That's a lot of dust. For context, a typical short-period comet like 67P/Churyumov-Gerasimenko produced similar rates near perihelion, but 67P is a well-studied body with a nucleus about 4 kilometers across. If 3I Atlas has a similar-sized nucleus, then 180 kilograms per second is plausible. But if the nucleus is smaller, say at 2 kilometers or less, then the dust production rate per unit surface area starts looking anomalously high. And here's where it gets tricky. We don't actually know the nucleus size with certainty. The coma obscures it. The best we have are indirect estimates based on brightness and assumed albedo. If you assume a typical cometary albedo of 4%, you get one nucleus size. Assume 10%, and the nucleus shrinks. The uncertainty range is wide enough that the dust production rate could be anywhere from reasonable to borderline absurd. So, we can't definitively say the numbers don't work. We can only say they're uncomfortable. They push the boundaries of what we'd expect from a natural comet of this type. There's another wrinkle. The dust production rate follows a power law with heliocentric distance. As the comet gets closer to the Sun, activity increases according to some exponent. For water-driven comets, that exponent is typically around -4, meaning activity quadruples for every halving of solar distance. For carbon monoxide or carbon dioxide-driven comets, the exponent can be steeper. 3I Atlas appears to have a steep power law, consistent with volatile ices other than water dominating the outgassing. That fits with the high carbon dioxide ratios we'll discuss later, but it also means that at closer distances the activity ramps up fast, and sustaining that level of outgassing over weeks or months requires a significant reservoir of volatiles. Now layer in the momentum budget. If you want to accelerate a 10-kilometer scale object by even a tiny fraction of a meter per second squared, you need to eject a lot of mass over time. Conservation of momentum is unforgiving. Every kilogram of gas expelled backward kicks the nucleus forward. Add up all the gas and dust observed over the entire trajectory, and you get a total mass loss. Compare that to the estimated total mass of the nucleus, and you start asking, can this object afford to lose that much material and still look active months later? Some researchers have proposed that 3I Atlas might have hidden jets. outgassing concentrated in specific active regions rather than uniformly across the surface. Jets are common on comets. We saw them on 67P/Churyumov-Gerasimenko up close. Jets can produce more thrust per unit mass loss, because the exhaust is directional rather than isotropic. If 3I Atlas has powerful jets pointing in favourable directions, the observed acceleration becomes easier to explain. But here's the catch. We don't see clear evidence of jets in most professional imagery. The NASA images show a featureless blur. UV observations show a roughly symmetric hydrogen envelope. Only the amateur reports suggest jets, and those reports aren't confirmed. This is where the plasma shield hypothesis starts to look relevant again. If the object is surrounded by a dense plasma environment that scatters light and hides surface features, then jets could exist, but remain invisible to high-resolution sensors. The amateurs, using longer exposures and different wavelengths, might be glimpsing those jets during moments when the plasma thins or shifts. If true, then the acceleration anomaly isn't really an anomaly. It's a mismatch between what we see and what's actually happening. The object is jetting vigorously, producing ample thrust, but we can't see the jets clearly because of plasma interference. The math works if the jets are there. The question is whether they're there. There are more, exotic explanations on the fringes. Some speculate that the acceleration might not be rocket-driven at all. What if 3I Atlas has a magnetic field, and interactions between that field and the solar wind generate forces? The solar wind is a plasma flow, and plasma plus magnetic fields equal complex dynamics. Magnetic pressure, magnetic tension, reconnection events, these can all produce forces, but the scale of the effect is usually small, relevant for tiny particles, not kilometre-sized bodies. To make magnetic forces matter at this scale, you'd need fields far stronger than what we've ever seen around a comet. You'd need something closer to a planetary magnetosphere, and that's not natural for a comet. Unless, of course, 3I Atlas isn't entirely natural. Let's not go down that rabbit hole yet. For now, the takeaway is this. The non-gravitational acceleration is real, measurable, and slightly uncomfortable given the observational constraints. It's not a smoking gun for anything exotic, but it's one more data point that doesn't quite fit the standard comet template. When you combine it with the visibility issues, the polarization anomalies, and the composition weirdness, you start to see a pattern. This object is at the edge of the distribution for every observable we measure. Maybe that's just because it's interstellar, formed in a different stellar nursery with different chemistry. Or maybe it's trying to tell us something, and we're not listening carefully enough. The math doesn't lie, but it doesn't always tell the whole truth either. Numbers are only as good as the assumptions behind them. If our assumptions about nucleus size, albedo, outgassing efficiency, or plasma interactions are off, then all the calculations shift. We could be looking at a perfectly ordinary comet through a distorted lens, or we could be looking at something genuinely anomalous through a clear lens. Until we get better data, higher resolution images, more complete spectroscopy, time-resolved photometry during the solar storm, we're stuck in this liminal space where the numbers are suggestive but not conclusive. They whisper that something's weird, but they don't shout what it is. And that's both frustrating and exhilarating because it means the mystery is still open, the investigations still live, and the next observation could tip the balance. Part 7. Polarization and surface properties. Now we turn to light itself, and specifically how light behaves when it bounces off 3I Atlas. Polarimetry is one of those underappreciated tools in the astronomer's kit. Less famous than spectroscopy, less visually dramatic than imaging, but incredibly revealing when you know how to read it. The basic idea is simple. Unpolarized light from the sun hits the comet, reflects off dust particles and ice grains in the coma, and becomes partially polarized in the process. By measuring the degree and orientation of that polarization, at different phase angles, the angle between the sun, the comet, and the observer, you learn about the size, shape, and composition of the scattering particles. 3I Atlas's polarimetric signature is, in a word, unprecedented. Researchers observing the object in visible wavelengths found a negative polarization branch, meaning at certain phase angles, the reflected light is polarized perpendicular to the scattering plane rather than parallel. This is common in comets and asteroids at small phase angles, but the depth and shape of 3I Atlas's negative branch are extreme. The polarization minimum hits around negative 2.7% at a phase angle near 7 degrees, and the inversion angle where polarization switches from negative to positive occurs around 17 degrees. To put that in context, most comets show negative polarization minimums between -1 and -2%, with inversion angles closer to 20 to 25 degrees. Asteroids typically have even shallower negative branches. 3I Atlas is off the charts, deeper minimum, steeper slope, earlier inversion. When you plot it against databases of comets and asteroids, it sits in empty parameter space. It's not just unusual, it's unique. What does this tell us? Polarization signatures depend on the optical properties of the scattering material, the complex refractive index, which encodes how light propagates through the substance, and the size, distribution and shape of particles. A deep negative polarization branch suggests particles with specific characteristics, possibly large grains, possibly icy surfaces, possibly particular compositions. Analysis suggests 3I Atlas might be rich in water ice, mixed with red organic compounds, resembling outer solar system bodies like trans-Neptunian objects, or Kuiper belt comets more than typical Jupiter family comets. This makes sense if you think about where 3I Atlas came from. It's interstellar. It formed around another star, possibly in that star's equivalent of the Kuiper belt, a cold, distant region where ices remain pristine and organics accumulate from cosmic ray irradiation. Objects in our own Kuiper belt are red and icy because they've spent billions of years in deep freeze, accreting organic tholins from radiation processing. If 3I Atlas has a similar history, then its polarization signature is a window into the surface conditions of exo-Kuiper belt objects. We're seeing, indirectly, what a planet-forming disk around another star produced in its outer reaches. But there's another angle to consider. Could the plasma environment we've been discussing affect polarization measurements? Plasma itself doesn't polarize light in the same way solid particles do, but charged dust grains, dust that's accumulated electric charge from the plasma environment, can behave differently than neutral grains. They can align with magnetic fields, creating systematic polarization patterns that wouldn't occur with neutral dust. If 3I Atlas's coma contains a mix of neutral and charged dust, the polarization signature might be composite, partly reflecting the intrinsic properties of the dust, partly reflecting the electromagnetic environment. This is speculative, admittedly. There's no direct evidence that charged dust is dominating the polarization signal. But it's worth considering because it ties back to the plasma shield hypothesis. If the object is surrounded by dense plasma, the dust entrained in that plasma would naturally become charged. The degree of charging depends on plasma temperature, density, and the UV radiation field. In principle, you could have dust grains with thousands of volts of surface potential, altering their optical behavior in subtle ways. The polarization data also hints at particle size. Large particles, grains bigger than the wavelength of light, say 1/10 of a millimeter or more, produce different scattering patterns than small particles. 3I Atlas appears to favour large grains, which aligns with the dust production estimates we discussed earlier. Large grains are harder to lift off the nucleus. They require stronger outgassing to overcome gravity, but once aloft, they persist longer in the coma because radiation pressure from sunlight is less effective at blowing them away. A coma dominated by large grains looks different than one dominated by small grains. Less blue scattering, more forward scattering, different colours. Put it all together, and you get a picture of an object with an old processed surface rich in water ice and organic compounds, shedding large dust particles into a coma that might be influenced by plasma interactions. The polarization signature is one more piece of the puzzle, one more way in which 3I Atlas stands apart from the crowd. It's not definitive proof of anything exotic, but it's consistent with the theme we've been developing. This is not your average comet. There's a microstory buried in the polarimetry. Imagine photons from the sun, 8 light minutes old, striking tiny ice crystals tumbling in the vacuum around 3I Atlas. Each photon scatters, its electric field vector rotating as it bounces. Some photons scatter toward Earth, carrying information encoded in their polarization state. Information about the crystal's size, shape, composition, charge. A telescope on Earth collects those photons, a polarimeter measures their alignment, and a scientist in a windowless office somewhere translates the numbers into physical properties. It's an act of decoding. We're reading the language of scattered light, trying to reconstruct a scene millions of kilometers away from clues carried by individual photons. and like any act of translation, it's imperfect. The polarization signal is noisy, dependent on observing geometry, sensitive to assumptions about scattering theory. The fact that ThreeI Atlas shows such an extreme signature means either the surface is genuinely weird, or we're misinterpreting the signal, or both. The data is real, but the interpretation is model dependent. Different scattering models yield different conclusions about particle size and composition. The deep negative branch could mean large icy grains, or it could mean fluffy aggregates with high porosity, or it could mean something else entirely that we haven't modelled yet. This uncertainty is maddening, but also central to the scientific process. We measure what we can measure, in this case polarization as a function of phase angle, and we infer what we can't measure directly: particle properties, surface composition, plasma interactions. Every inference rests on a chain of assumptions, and if any link in that chain is wrong, the conclusion shifts. The polarization data tells us ThreeI Atlas is unusual. It doesn't tell us exactly why. To answer that, we need more data: spectroscopy to confirm composition, imaging to resolve particle structures, in situ measurements from a flyby mission. Until then, we're interpreting shadows on the wall of Plato's cave, trying to guess the shape of the thing casting them. Part 8. Composition, CO2, cosmic rays and exotic chemistry. Time to dive into the chemistry, because this is where ThreeI Atlas goes from unusual to outright bizarre. When the James Webb Space Telescope turned its infrared eye toward the object, astronomers weren't sure what to expect. Webb's sensitivity in the near-infrared allows it to detect molecular absorption and emission features that reveal the composition of the coma, what gases are boiling off the nucleus as it heats up. For comets, water vapour usually dominates. It's the most abundant volatile ice in the solar system, and most comets are basically dirty snowballs with water as the primary constituent. ThreeI Atlas didn't get the memo. Webb's near-spec instrument, operating from 0.6 to 5.3 micrometers, captured spectra showing an extreme carbon dioxide to water ratio, roughly 8:1. For every water molecule evaporating from the nucleus, 8 carbon dioxide molecules are coming off. That's insane by solar system standards. Typical long-period comets from the Oort cloud show carbon dioxide to water ratios closer to 0.03 to 0.2. Jupiter family comets are similar. Even other Oort cloud comets with elevated carbon dioxide rarely exceed ratios of 1. ThreeI Atlas is 6 standard deviations outside the normal distribution. It's a statistical outlier so extreme that you'd expect to see it once in hundreds of millions of trials if comets are drawn from a single population. What could explain this? One possibility is that ThreeI Atlas formed in a region of its parent protoplanetary disk, where carbon dioxide ice was more stable than water ice. In our solar system, water ice dominates beyond the snowline at a few astronomical units, but carbon dioxide ice requires colder temperatures to condense. There's a carbon dioxide ice line farther out, maybe around 10 or 20 astronomical units depending on disk conditions. If ThreeI Atlas formed beyond that line, it could have accreted more carbon dioxide relative to water. That would make it a cold outer disk object, analogous to our Kuiper belt or scattered disk populations. But there's another explanation, more exotic and maybe more plausible: cosmic ray processing. Imagine ThreeI Atlas drifting through interstellar space for millions or billions of years. It's cold, dark, isolated, far from any star's warmth, and it's being bombarded constantly by high-energy particles, cosmic rays, mostly protons travelling at near light speed, remnants of supernovae and other violent cosmic events. When a cosmic ray slams into the surface ice of the object, it deposits energy, breaking molecular bonds and triggering chemical reactions. One well-studied reaction in this context is the conversion of carbon monoxide to carbon dioxide. If the original ice mix included carbon monoxide, cosmic rays can oxidize it over time, turning CO into CO2. Simultaneously, the radiation processing creates complex organic molecules, tholins, long-chain hydrocarbons, nitrogen-bearing compounds that form a dark, reddish crust on the surface. This crust acts as an insulating layer, protecting the underlying ice but also altering how the nucleus outgasses. When the comet eventually enters a solar system and starts to warm up, the carbon dioxide sublimates preferentially because it's more volatile than water. The water ice might be locked beneath the organic crust, sublimating more slowly. This scenario fits multiple observations at once. The high carbon dioxide to water ratio? Check. The red colour and polarization signature suggesting organic rich surface? Check. The large dust grains, possibly chunks of that organic crust breaking off? Check. The unusual activity profile with steep power law dependence on solar distance? Check. Cosmic ray processing over billions of years turns a relatively ordinary icy body into something chemically strange, and when it finally gets near a star again, it behaves differently than a fresh comet. There's supporting evidence for this idea from studies of dust production. Analysis suggests ThreeI Atlas sheds predominantly large grains, around 0.1 millimeters in size. Small grains, which would normally dominate in a typical cometary coma, seem depleted. This could be because the organic crust makes the dust sticky. Interparticle cohesion holds small grains together into larger aggregates. When the surface erodes, it doesn't produce fine dust but rather chunky debris. It's like the difference between sand and gravel. One flows easily, the other clumps. The James Webb data also revealed absorption features consistent with water ice, and possibly other volatile ices, but the carbon dioxide overwhelmed the signal. Follow-up observations in other wavelengths. Mid-infrared radio could detect additional species: carbon monoxide, methane, ammonia, hydrogen cyanide. Each new detection adds a line to the chemical inventory, helping us reconstruct the conditions under which ThreeI Atlas formed and the processing it underwent during its long journey through the interstellar medium. But here's where it gets philosophically interesting. If cosmic ray irradiation over billions of years can produce such dramatic chemical changes, creating an organic crust and altering volatile ratios, then every interstellar object should arrive in our solar system pre-processed in similar ways. Yet, 2I/Borisov, the previous interstellar comet, looked fairly normal. Carbon monoxide present but not extreme. Carbon dioxide to water ratios within the broad distribution of solar system comets. Why is ThreeI Atlas so different? Did it spend longer in interstellar space? Did it form with a different initial composition? Or is the cosmic ray processing theory incomplete? One wild card is the possibility that ThreeI Atlas's composition isn't entirely natural. If you wanted to design a spacecraft to survive interstellar transit, you might coat it in a protective layer of ice and organics to shield the interior from radiation and micrometeorite impacts. That icy shell would chemically evolve over time, accumulating cosmic ray damage and becoming carbon dioxide rich. When the object entered a solar system and the ice started sublimating, it would look almost exactly like a comet, just a weird one. This is the terrain where natural and artificial explanations start to overlap uncomfortably. The chemistry we're seeing could be entirely natural, a consequence of known processes acting over long timescales, or it could be natural chemistry employed as camouflage. To be absolutely clear, there's no evidence ThreeI Atlas is artificial. None. The composition is unusual but not impossible to explain through natural means. But the fact that the two explanations produce similar observables is worth noting. It means chemistry alone can't rule out artificial hypotheses. You'd need other evidence: clear geometric structures, anomalous accelerations that can't be explained by outgassing, radio emissions with information content, something unambiguous. We don't have that. What we have is a comet that looks mostly like a comet but keeps showing up at the edges of the bell curve for every property we measure. The carbon dioxide mystery is just one more edge case data point. Combined with the acceleration anomaly, the polarization signature, the visibility paradox, and everything else, it paints a picture of an object that's consistently inconsistent, always plausible, never quite comfortable. And that's the space where interesting science happens, where our models get tested and sometimes break, where we're forced to ask whether we're seeing something genuinely new or just variations on familiar themes distorted by incomplete data and selective attention. Part 9. Alternative theories, artificial origins and cloaking. Let's acknowledge the elephant in the observatory. For some people, including a few credentialed scientists willing to risk their reputations, ThreeI Atlas isn't a comet at all. It's a probe, a craft, a visitor in the most literal and unsettling sense. The idea isn't new. When 1I/Oumuamua accelerated unexpectedly as it left the solar system, Harvard astronomer Avi Loeb publicly speculated that it might be a light sail, a piece of alien technology catching the solar wind for propulsion. The mainstream scientific community responded with a mixture of skepticism and irritation, proposing natural mechanisms like hydrogen outgassing to explain the acceleration. But Loeb persisted, and a certain segment of the public latched onto the possibility with enthusiasm. Now, with ThreeI Atlas, the artificial origin hypothesis is back. The case, as its proponents lay it out, goes something like this. The object exhibits multiple anomalies that strain natural explanations: unusual trajectory, high carbon dioxide, deep polarization branch, non-gravitational acceleration, and visibility issues that suggest obscuration or cloaking. Taken individually, each anomaly can be explained away. Taken together, they form a pattern that some interpret as evidence of design. Maybe ThreeI Atlas is an interstellar probe coated in ice and organics to mimic a comet, travelling through the galaxy on a slow survey mission. Maybe the plasma shield we've been discussing isn't accidental but engineered, a deliberate stealth feature to avoid detection or mimic natural phenomena. The mainstream counter-argument is straightforward and powerful. NASA, ESA, and the broader astronomy community insist that ThreeI Atlas looks like a comet and behaves like a comet. Yes, it's unusual, but unusual is not impossible. The galaxy contains trillions of comets. Statistically, some will be outliers. The fact that ThreeI Atlas shows properties at the edge of known distributions doesn't mean it's artificial. It means our sample size of interstellar objects is still tiny, and we're seeing the natural diversity of exocometary populations. Extraordinary claims require extraordinary evidence, and a fuzzy image plus some weird chemistry doesn't meet that bar. Both sides have valid points. The artificial hypothesis suffers from a lack of smoking gun evidence. There's no detected signal, no geometric perfection, no clear violation of physical law that would force an artificial conclusion. Everything about ThreeI Atlas can, with effort and some assumptions, be explained naturally. But the natural hypothesis also requires a certain amount of special pleading. Why is every observable property slightly weird? Why does this one object happen to be an outlier in multiple independent ways? Coincidence? Or are we missing something? One variant of the artificial hypothesis is particularly relevant to our discussion: the cloaking theory. Suppose you're an advanced civilization sending probes into other star systems. You might not want those probes to be immediately obvious. Maybe you design them to look like natural objects, asteroids, comets, to avoid triggering alarms or attracting attention. A plasma shield that blurs high-resolution imagery while allowing passive observation would be an ideal stealth feature. It makes the probe visible enough to avoid collisions and suspicions of total invisibility, but obscure enough to prevent detailed scrutiny. The visibility paradox in this interpretation isn't a bug, it's a feature. This sounds like science fiction, and maybe it is, but it's not physically absurd. We know that plasma can scatter light. We know that magnetic fields can trap and control plasma. If you could generate a stable, dense plasma envelope around an object using onboard power or harvested solar wind energy, you'd effectively have an electromagnetic cloak. It wouldn't make you invisible, but it would degrade observational resolution, especially for high-frequency sensors. Longer wavelengths, radio, infrared, might penetrate better, but by that point you've already confused most observers. The problem with evaluating this hypothesis is that it's not falsifiable in the traditional sense. Any anomaly can be interpreted as either natural weirdness or deliberate design. The object accelerates, natural outgassing, or thrusters, weird chemistry, cosmic ray processing, or deliberate camouflage, plasma obscuration, solar wind interaction, or active cloaking. Without a signal, a message, an unambiguous artifact, you can't prove artificiality. And you also can't disprove it, because absence of evidence isn't evidence of absence when the evidence might be hidden. This epistemological trap frustrates rigorous scientists, and rightly so. Science advances by testing hypotheses that make specific, falsifiable predictions. The artificial origin hypothesis, as typically framed, doesn't. It's a just-so story that fits any data because it's flexible enough to accommodate anything. That doesn't make it wrong. Reality doesn't care about our methodological preferences, but it makes it scientifically unproductive. You can't design an experiment to test maybe aliens. Or can you? There are, in fact, testable predictions. If ThreeI Atlas has an active cloaking system, It requires power. That power must come from somewhere. Radioactive decay, solar panels, chemical reactions, something. Power generates heat, and heat produces infrared signatures. High-resolution infrared spectroscopy could detect anomalous thermal emissions inconsistent with passive solar heating. If the object is warmer than it should be given its distance from the sun, that's a red flag. Similarly, magnetic field measurements, if we could get close enough, would reveal whether the plasma shield is sustained by artificially generated fields or natural solar wind interactions. Radio observations are another angle. If the object has any electronic systems, even if shielded, there's a non-zero chance of detectable electromagnetic leakage. The recent detection of radio emissions from ThreeI Atlas was attributed to hydroxyl radicals, a natural process. But what if there's a faint carrier wave buried in the noise? What if, in the terabytes of data collected by radio telescopes like Meerkat, there's a pattern no one's noticed yet? This is where citizen science and AI come into play, combing through data for anomalies that automated pipelines might miss. The artificial origin hypothesis also makes social and psychological predictions. If ThreeI Atlas were confirmed as artificial, the impact on human civilization would be profound. First contact, even if indirect, just detecting a probe, not communicating with its makers, would reshape our understanding of our place in the cosmos. Some argue that governments or space agencies, aware of this potential, might downplay or obfuscate anomalies to prevent panic or premature conclusions. This feeds into the conspiracy angle, where blurry NASA images aren't failures but deliberate choices. I don't buy the conspiracy. Having worked adjacent to space science communities, I know they're populated by people genuinely excited about discovery, not shadowy gatekeepers hoarding secrets. If ThreeI Atlas were artificial, someone would leak it. The scientific community is too distributed, too international, too leaky for a cover-up, but the psychology matters. The public's hunger for confirmation of alien intelligence creates a filter bubble, where ambiguous data gets interpreted optimistically. Every anomaly becomes a clue, every unexplained feature becomes evidence. Meanwhile, the scientific establishment, burned by past false alarms and wary of reputational damage, leans hard the other way, dismissing even legitimate anomalies as noise. The truth probably lies in the messy middle. ThreeI Atlas is almost certainly natural, a comet with unusual but explicable properties shaped by its origin in another stellar system and billions of years of interstellar processing. But almost certainly isn't definitely, and that gap is where speculation thrives. As long as the object remains blurry, as long as observations remain incomplete, as long as questions outnumber answers, the artificial hypothesis will persist. And maybe that's okay. Maybe entertaining uncomfortable possibilities, even ones we ultimately reject, keeps us honest and prevents us from prematurely closing the case. Because here's the thing, if we ever do detect genuine alien technology, it probably won't announce itself with neon lights and radio messages. It'll look like an anomaly, a statistical outlier, something that almost makes sense naturally but doesn't quite fit. And if we've trained ourselves to reflexively explain away every anomaly, we'll miss it. The challenge is to remain skeptical enough to avoid false positives, but open enough to recognise true positives when they arrive. ThreeI Atlas is practice for that challenge, a test case in how we evaluate the boundary between natural and artificial, expected and extraordinary. Whether it's a comet or a probe, the lessons we learn from investigating it will matter when the next interstellar visitor shows up, and given the detection rates we're seeing, the next one won't be far behind. Part 10, Visibility Mechanisms, How Plasma Could Obscure or Scatter Light. Let's dig deeper into the physics of how plasma actually hides things, because if the plasma shield hypothesis has any merit, we need to understand the mechanisms in detail. Plasma is electrically conductive, meaning it responds to electromagnetic fields. When light, which is just oscillating electric and magnetic fields, passes through plasma, the charged particles in the plasma react. Electrons, being light and mobile, oscillate in response to the light's electric field. Those oscillations generate secondary electromagnetic waves that interfere with the original light, causing scattering, absorption, and refraction. The key parameter governing how plasma interacts with light is the plasma frequency, which depends on electron density. Below the plasma frequency, light can't propagate through the plasma, it gets reflected. Above the plasma frequency, Light passes through, but gets refracted, bent like light through glass, but in ways that depend on wavelength and electron density. For a typical cometary plasma with electron densities of 10 to the 4 or 10 to the 5 per cubic centimetre, the plasma frequency falls in the radio to microwave range. That means radio waves get scattered or absorbed, while visible and UV light mostly pass through, though with some scattering from collisions and refractive bending. But we're proposing something denser, a plasma shield with electron densities perhaps 10 to the 6 or higher, comparable to the densest regions of Earth's ionosphere. At those densities, even visible light starts experiencing significant interaction. Scattering increases. Absorption becomes non-negligible, especially at shorter wavelengths like UV. The plasma effectively becomes a translucent fog, letting some light through, but diffusing it, spreading it out, reducing contrast and resolution. Sharp features like jets or surface details blur into a general glow. There's another effect called Faraday rotation, where the plane of polarization of light rotates as it passes through magnetized plasma. If ThreeI Atlas is surrounded by plasma threaded with magnetic fields, light emerging from the nucleus would have its polarization rotated by amounts depending on the path length through the plasma, the magnetic field strength, and the electron density. This could complicate polarimetry measurements, adding an artificial signature on top of the natural polarization from dust scattering. In principle, careful analysis could disentangle the two effects, but it requires knowing the magnetic field geometry, which we don't. Scattering in plasma also depends on wavelength. Shorter wavelengths scatter more strongly. This is why Earth's sky is blue. Shorter blue wavelengths scatter more than longer red wavelengths. In a dense plasma, UV light would be scattered far more than red or infrared light. This creates wavelength-dependent visibility. An object might look blurry and featureless in UV but show structure in the infrared. If HiRISE observes primarily in visible wavelengths, while amateur telescopes use red filters or infrared-sensitive CCDs, they'd see different things even looking at the same object. Integration time matters hugely here. A brief exposure captures a snapshot, and if that snapshot happens during a moment when plasma density is high, or turbulence is scattering light chaotically, the image is blurry. A long exposure averages over time, smoothing out short-term fluctuations and integrating more photons, which can reveal faint features that brief exposures miss. Amateur telescopes often use exposures lasting minutes, stacking dozens of frames to build signal-to-noise. HiRISE, imaging a moving target from a moving platform, uses much shorter exposures, milliseconds to seconds, to avoid motion blur. The trade-off is that short exposures capture less light and are more vulnerable to instantaneous plasma conditions. There's also the question of vantage point. MRO observes ThreeI Atlas from Mars orbit, roughly 30 million kilometers away, at a specific geometry relative to the Sun. Amateur observers on Earth are at different distances and angles. The plasma environment around the comet isn't uniform. It's denser on the sunward side where ionization is strongest, sparser on the tail side. Depending on the line of sight, observers might look through more or less plasma. Someone observing edge-on, looking along the plasma tail, would see different scattering than someone viewing face-on, looking directly at the sunward coma. This geometric effect could explain why different observers report different structures. They're literally looking through different amounts of plasma. Then, there's temporal variability. The solar wind isn't constant. It varies with solar activity, with sector boundaries in the Sun's magnetic field, with the passage of high-speed streams and coronal mass ejections. As the solar wind pressure on ThreeI Atlas changes, the plasma environment adjusts, compressing when pressure increases, expanding when it decreases. These changes happen on timescales of hours to days. If HiRISE imaged the object during a high-pressure interval when the plasma was compressed and dense, it would see maximum obscuration. If amateur astronomers observed a day earlier during a lull, they'd see clearer structure. Everyone's telling the truth about what they saw, but they're seeing snapshots of a dynamic system in different states. Now let's address challenges to the plasma shield hypothesis, because any good scientific investigation requires steel-manning the counter-arguments. First, energy. Maintaining a dense, stable plasma shell requires energy input. You need continuous ionization to replace electrons and ions that recombine back into neutral atoms. The Sun provides some of this through UV radiation, and the solar wind. But is it enough? For a typical cometary coma, yes, the ion tail is a well-known plasma feature sustained by solar input. But for a much denser, more extensive shield, you'd need proportionally more energy. Where does it come from? One possibility is that ThreeI Atlas's high carbon dioxide outgassing provides the raw material. Carbon dioxide ionizes relatively easily, and if the outgassing rate is as high as the acceleration data suggests, there's plenty of gas to ionize. The solar UV flux at roughly 1.5 astronomical units is intense enough to maintain significant ionization rates. Combined with solar wind electrons impacting the coma, you could plausibly generate and sustain a dense plasma envelope. It wouldn't be stable forever. As the comet recedes from the Sun, ionization rates drop and the plasma fades, but during the active phase near perihelion, it could persist. Second challenge, spectroscopic signatures. If there's dense plasma, we should see bright emission lines from ionized species, CO+, CO2+, H2O+, and so forth. Some emission has been detected in UV observations, consistent with normal cometary ion tails. But the intensity isn't dramatically higher than expected for a comet of this brightness. There's no smoking gun of extreme ionization. However, emission line intensity depends on viewing geometry and the plasma's temperature and density distribution. If the densest plasma is concentrated close to the nucleus, and that region is obscured by dust and neutral gas, the emission might be partially self-absorbed or diluted in ground-based spectra that integrate over large areas. High spatial resolution spectroscopy, which we don't have yet, could reveal plasma emission concentrated near the nucleus. Third challenge, radio observations. The recent detection of hydroxyl radio emission from ThreeI Atlas is consistent with normal cometary activity, water molecules breaking apart to form hydroxyl radicals. But hydroxyl emission doesn't probe the densest regions near the nucleus. It samples the outer coma where gas has expanded and cooled. If there's a plasma shield, it would be most evident in radio scattering or dispersion effects, signals that pass through the plasma getting delayed or spread in frequency. So far, no such effects have been reported. But again, the radio data is early and not focused on searching for plasma effects. A dedicated campaign measuring dispersion across multiple frequencies could test this prediction. Fourth challenge, stability. Plasma is notoriously unstable. Left to its own devices, plasma tends to develop waves, turbulence, and instabilities that break up uniform structures. Maintaining a smooth, shell-like plasma envelope requires either very specific conditions, low temperature, high density, strong magnetic field, or continuous input to suppress instabilities. In the dynamic environment around a comet, buffeted by the solar wind and fed by irregular outgassing, you'd expect the plasma to be lumpy and variable rather than forming a clean shield. This doesn't invalidate the hypothesis. A turbulent, patchy plasma fog could still degrade imaging, but it makes the concept less elegant and harder to model. So, where does this leave us? The plasma shield hypothesis is plausible, but not proven. The physics works in principle. Dense plasma can scatter and absorb light in wavelength and geometry-dependent ways. Cometary outgassing can supply the raw material, and solar radiation can maintain ionization. The temporal and spatial variability of the plasma could explain the visibility paradox, different observers seeing different things at different times. But the evidence is circumstantial. We need direct detections, spatially resolved spectroscopy showing plasma emission near the nucleus, radio observations revealing dispersion, infrared imaging showing the thermal signature of ionized gas. Until we have those, the hypothesis remains speculative. Yet speculation has value. It forces us to think about observational biases and instrumental limitations. It reminds us that the space between observer and target isn't empty. It's filled with dynamic, ionized gas that interacts with light in complex ways. Even if the plasma shield hypothesis is wrong in detail, the broader point stands. What we see depends not just on the object, but on the medium through which we see it and the tools we use to look. ThreeI Atlas is teaching us that seeing is harder than we thought, that clarity is a luxury we can't always afford, and that sometimes the blur contains as much information as the sharpness, if only we learn how to read it. The analogy I keep coming back to is atmospheric turbulence. Astronomers have long known that Earth's atmosphere blurs images, which is why we build telescopes on mountaintops and launch them into space. But turbulence isn't uniform, it varies with altitude, wavelength, time, and observing angle. Adaptive optics systems compensate in real time using deformable mirrors to undo the atmospheric distortion. The result is clear images from ground-based telescopes that rival space telescopes in some wavelengths. Could we do something similar for plasma? Could we model the expected plasma scattering and computationally remove it, deblurring images of ThreeI Atlas the way we deblur atmospheric seeing? In principle, yes. In practice, it's fiendishly difficult. You need to know the plasma's density, temperature, magnetic field, and velocity structure along the line of sight. You need spectroscopic data to constrain ionization states. You need time-resolved observations to map variability. It's an inverse problem, reconstructing the three-dimensional plasma distribution from two-dimensional images and one-dimensional spectra. Hard, but not impossible. And if we succeed, we might not just see ThreeI Atlas more clearly, we might develop techniques applicable to other obscured objects, from dust-shrouded stars to plasma-wrapped exoplanets transiting distant suns. This is the frontier. Not just discovering new objects, but learning new ways to see them. ThreeI Atlas, blurry and ambiguous as it is, might be the catalyst for a methodological leap. Sometimes you learn more from what you can't see than from what you can. The blur itself is data, a signature of the environment, a challenge to our assumptions. If we rise to that challenge, if we build better models and better instruments and better analysis techniques, then the visibility paradox won't be a frustration. It'll be an opportunity, an invitation to look harder, think deeper, and accept that the universe doesn't always cooperate with our desire for clean answers. Sometimes it gives us plasma instead. Part 11. Radio emissions from ThreeI Atlas. While optical telescopes have been squinting at ThreeI Atlas and seeing mostly blur, radio astronomers have been listening, and they're hearing something. In late November 2025, the Meerkat Radio Telescope Array in South Africa detected radio emissions from the comet at 18 centimetre wavelengths. This isn't unusual in itself. Comets commonly emit radio waves at specific frequencies corresponding to molecular transitions, and the detection here was attributed to hydroxyl radicals, OH molecules produced when water vapour is broken apart by solar UV radiation. Hydroxyl emits at 4 characteristic frequencies near 1.667 GHz, sometimes called the main lines of the OH radical. When a comet outgasses water, some fraction of those water molecules photodissociate into hydrogen and hydroxyl within hours of leaving the nucleus. The hydroxyl molecules, freshly created and out of thermal equilibrium, populate excited rotational states that decay by emitting radio photons at those specific frequencies. It's a diagnostic of water production rate. More water means more hydroxyl means stronger radio emission. Detecting this from ThreeI Atlas confirms the object is actively outgassing water, which aligns with its classification as a comet. But let's dig into what this tells us about the plasma shield hypothesis. Radio waves interact with plasma differently than visible light. At frequencies below the plasma frequency, radio waves can't propagate, they're reflected. At frequencies above it, they pass through but experience dispersion and scattering. For the radio emission detected at 1.667 GHz, we're well above the plasma frequency for typical cometary plasma, so the signal should mostly get through. However, if the plasma is dense enough, radio waves will still experience phase delays and scatter broadening. Phase delay happens because plasma has a refractive index that depends on frequency and electron density. Radio waves passing through plasma travel slightly slower than the speed of light, and the delay is proportional to the integral of electron density along the line of sight. This is measurable. Pulsars, for instance, show frequency-dependent arrival times due to dispersion in the interstellar medium, a phenomenon called the dispersion measure. If ThreeI Atlas has a dense plasma shell, radio photons from hydroxyl emission near the nucleus would be delayed compared to photons from the outer coma. Multi-frequency observations could detect this as a frequency-dependent time delay, or spectral broadening. So far, no unusual dispersion has been reported. The hydroxyl lines appear at the expected frequencies without anomalous broadening or splitting. This is a point against the extreme version of the plasma shield hypothesis. If the shield were incredibly dense, we'd expect to see radio signatures. But it's not a fatal blow. The hydroxyl emission originates from the outer coma, tens of thousands of kilometers from the nucleus, where the plasma has already expanded and cooled. If the densest plasma is concentrated close to the nucleus, within a few hundred or thousand kilometers, the hydroxyl photons might be generated outside that region, and therefore don't sample it. Radio emissions from the inner coma, if detectable, would be the real test. There's another angle here. What if the radio detection itself is anomalous in subtle ways we haven't recognized? The reported emission is consistent with hydroxyl, but hydroxyl lines can be affected by non-standard pumping mechanisms. Normally solar UV photons pump the hydroxyl molecules into excited states, which then decay and emit radio photons. But in a dense plasma environment, collisional excitation, hydroxyl molecules getting excited by colliding with electrons or ions, could alter the line ratios and intensities. The four hydroxyl lines normally have characteristic relative intensities, but those ratios can shift if the excitation mechanism changes. Careful analysis of the line ratios might reveal non-standard conditions indicative of unusual plasma density or temperature. Additionally, if the magnetic field around ThreeI Atlas is strong enough, Siemens splitting could occur. The hydroxyl lines split into multiple components due to the interaction between the magnetic field and the molecule's magnetic moment. The splitting is tiny, on the order of kilohertz for fields of milligauss strength, but detectable with high spectral resolution. So far, no Siemens splitting has been reported, which constrains the magnetic field near the hydroxyl emission region to be relatively weak. Again, this doesn't rule out a plasma shield with embedded magnetic fields closer to the nucleus, but it limits how strong those fields can be in the outer coma. Radio observations also offer a way to probe the nucleus itself, or at least the inner coma. Continuum radio emission, broadband emission not tied to specific molecular lines, can arise from thermal emission from dust grains or from non-thermal processes like synchrotron radiation. Dust grains, even tiny ones, emit radio waves if they're warm enough, though the signal is faint. If ThreeI Atlas has a lot of large dust grains close to the nucleus, as the polarimetry suggests, those grains should produce detectable continuum emission at centimetre wavelengths. Measuring that continuum would constrain the dust mass and temperature distribution. More exotically, if there's a dense plasma with energetic electrons, electrons accelerated to relativistic speeds by magnetic reconnection or other processes, those electrons spiraling in magnetic fields would emit synchrotron radiation. Synchrotron emission is polarized and has a characteristic spectrum. It's common in active galactic nuclei and supernova remnants, but not typically seen in comets. If detected from ThreeI Atlas, it would be a smoking gun for unusual plasma processes. No such detection has been made, but again, we're early in the observational campaign. Dedicated radio surveys across multiple frequencies and polarization states could reveal surprises. The radio detection also connects to a broader question. How transparent is the coma to different wavelengths? We've been discussing visibility primarily in optical terms. Can telescopes see the nucleus and jets through the dust and plasma? But transparency is wavelength dependent. Dust that blocks visible light might be transparent at longer wavelengths. Radio waves, with wavelengths of centimetres to metres, are unaffected by sub-millimetre dust grains. They sail right through. That's why radio observations can peer into dense molecular clouds or dusty star-forming regions that are opaque in visible light. If ThreeI Atlas's coma is optically thick, dust and plasma blocking visible light, it should still be transparent at radio wavelengths. The fact that we detect hydroxyl emission confirms this. But here's a thought experiment. What if the nucleus itself is bright at radio wavelengths? Not from hydroxyl, but from thermal continuum or some other process. If you could image ThreeI Atlas at high resolution in the radio, would you see a clear point source at the nucleus position, unobscured by plasma or dust? In principle, yes. Radio interferometry, using arrays like ALMA or the VLA, could achieve sub-arc second resolution, potentially resolving the nucleus, or at least the inner few thousand kilometres. Such observations haven't been reported yet, possibly because the object is faint at radio wavelengths, or because telescope time is scarce. But they're feasible, and would provide a crucial test. If radio imaging shows clear structure where optical imaging shows blur, that's strong evidence for wavelength-dependent obscuration, exactly what the plasma shield hypothesis predicts. There's also the question of time variability. If the plasma shield fluctuates due to changes in solar wind pressure or outgassing rate, the radio emissions might vary in intensity or spectral shape. Hydroxyl production rate depends on water outgassing, which in turn depends on solar heating and nucleus rotation. Most comets show periodic brightness variations as active regions rotate in and out of sunlight. If 3I Atlas has a rotation period of hours to days, the hydroxyl emission should modulate accordingly. Monitoring the radio signal over time could reveal that periodicity and constrain the nucleus's spin state. Sudden changes, spikes, or dips in emission might correlate with plasma disturbances or outbursts. So the radio detection is both confirmation and tantalizing clue. It confirms 3I Atlas is outgassing water like a comet. It provides a new observable hydroxyl emission that can be monitored over time, and it opens avenues for deeper investigation, dispersion measurements, line ratio analysis, continuum searches, interferometric imaging. Radio astronomy often plays second fiddle to optical in public consciousness, but for studying obscured objects it's the superior tool. Radio waves cut through the fog. If the plasma shield hypothesis has merit, radio observations will be the ones that ultimately test it, revealing whether the inner coma is as strange as the outer coma appears. And there's poetry in that. The universe speaks in many languages: visible light, infrared heat, radio whispers, gamma-ray shouts. We've built instruments to listen across the spectrum, but we don't always know which language will tell the clearest story. For 3I Atlas, visible light gives us riddles and blur. Radio gives us clarity, at least for hydroxyl. Maybe the answer to the visibility paradox isn't to look harder in the wavelengths that confuse us, but to look smarter in the wavelengths that don't. Maybe the comet is teaching us to diversify our senses, to not rely on optical sight alone, but to triangulate truth across the electromagnetic spectrum. That's a lesson applicable far beyond this one object, a methodological insight that will matter when the next interstellar stranger arrives and challenges us to see it truly. Part 12. China's Tianwen-1 Images and Geopolitical Science. While NASA dominates headlines, there's another player in the 3I Atlas observation game, China's Tianwen-1 mission, currently orbiting Mars with its high-resolution imaging camera. Reports suggest Tianwen-1 also captured images of the interstellar comet, though the data release has been less publicised than NASA's. This isn't surprising. China's space program operates with different transparency norms, and international cooperation in space science is often complicated by geopolitical tensions. But it raises interesting questions about who sees what, who publishes when, and whether the visibility paradox is partly a data access paradox. China's space capabilities have grown explosively over the past 2 decades. From lunar landings to Mars rovers to plans for a space station rivaling the ISS, the Chinese National Space Administration operates on a scale comparable to NASA. Tianwen-1, launched in 2020, successfully placed an orbiter and rover at Mars, making China only the second nation after the United States to operate a rover on the Martian surface. The orbiter carries multiple cameras, including the HIRIC instrument, high-resolution imaging camera, capable of resolutions similar to NASA's HiRISE. If Tianwen-1 imaged 3I Atlas from a different vantage point or at different times than MRO, the images might show different features. Remember, the plasma environment and viewing geometry affect what's visible. Tianwen-1's orbit differs from MRO's, meaning different lines of sight to the comet. If China releases those images, and that's a big if, given their selective approach to data sharing, they could provide crucial comparison. Are the images similarly blurry, supporting the idea that the object is intrinsically obscured? Or do they show structure that NASA's images missed, suggesting the blur is geometry dependent? This brings us to the uncomfortable topic of data transparency. NASA operates under mandates requiring eventual public release of all science data, typically after a proprietary period for the science teams. Anyone can access Hubble or Webb data archives, download raw files, and conduct independent analysis. This openness is a cornerstone of modern astronomy, enabling reproducibility and democratic participation. But it's not universal. Some space agencies, particularly those in countries with authoritarian governments or military space programs, treat data as strategic assets. Images might be classified, embargoed, or released selectively. China's approach falls somewhere in the middle. They release significant data, lunar samples, Martian surface images, scientific papers in international journals, but the process is often slower and more opaque than NASA's. There's no equivalent of NASA's planetary data system, a comprehensive open archive. Instead, data trickles out through official channels, press releases, and scientific collaborations. This creates an asymmetry. Western astronomers scrutinize every NASA pixel in real time, while Chinese data might not be fully accessible for months or years. For 3i Atlas, this matters. If amateur astronomers are seeing jets and rings that NASA's sensors don't show, but Chinese sensors do show, that's significant evidence. It would suggest the visibility paradox is instrument or geometry specific rather than object intrinsic. Conversely, if Tianwen-1's images are equally blurry, it strengthens the case that something about the object itself resists high-resolution imaging. We need that comparison, but we might not get it on a useful timescale. By the time Chinese data is publicly released, 3i Atlas will have moved on, and the moment for real-time analysis will have passed. There's also a geopolitical subtext. Space exploration, for all its rhetoric of peaceful international cooperation, remains entangled with nationalism and competition. The race to observe and characterize interstellar objects isn't just scientific, it's symbolic. Who gets there first? Who produces the clearest images? Who publishes the definitive paper? These questions matter for funding, prestige, and soft power. If China were to release stunning images of 3i Atlas showing structure that NASA missed, it would be both a scientific contribution and a geopolitical statement. We're equals or superiors in this domain. Conversely, if NASA's images remain the best available, despite being blurry, it reinforces perceptions of American technological dominance. This competition can drive progress. Nations invest more in space programs to keep up or get ahead. But it can also hinder collaboration. Data that might be shared freely in a cooperative framework gets hoarded or released strategically. Scientists who would benefit from pooling observations face barriers of classification, language, and bureaucracy. Amateur astronomers, interestingly, sidestep much of this. They operate outside national programs, sharing data freely on forums and social media. A telescope in Australia captures an image, someone in Europe processes it, a programmer in Canada writes software to enhance it, and they all compare notes on Reddit. This grassroots network is faster and more open than official channels, though less rigorous in terms of calibration and peer review. For 3i Atlas, the amateur community might end up being the most transparent and collaborative observers, ironically making their data, disputed though it is, more accessible than government missions costing billions. There's a broader question here about the future of interstellar object science. As detection rates increase, we're now finding roughly one interstellar object per year, and that rate will climb as survey telescopes improve. The need for coordinated, open observation campaigns becomes critical. Interstellar objects move fast. They're only observable for weeks or months. If data is siloed in national programs or delayed by proprietary embargoes, opportunities are lost. The Vera Rubin Observatory, set to begin operations soon, will detect dozens or hundreds of interstellar objects per year. Managing that flood of discoveries will require international frameworks for rapid data sharing and coordinated follow-up. Some progress is being made. The International Astronomical Union's Minor Planet Center serves as a clearinghouse for asteroid and comet observations, aggregating data from professional and amateur sources worldwide. Alerts go out within hours of a discovery, enabling rapid follow-up. But this works only if participants share data promptly. A nation or agency that sits on observations for strategic reasons breaks the chain. Science suffers, and our collective understanding of these rare visitors diminishes. For 3i Atlas specifically, the ideal scenario is full transparency from all observers, NASA, China, ESA, amateurs, everyone. Pull the imagery from different vantages, different wavelengths, different times. Build a complete multi-angle, multispectral dataset. Model the plasma environment, the dust distribution, the nuclear activity. Test hypotheses against comprehensive data rather than fragments. This is how science should work. But it requires trust, cooperation, and a shared commitment to knowledge over competition. In our current geopolitical climate, that's aspirational rather than assured. Still, there are reasons for optimism. Science has a way of transcending politics, at least sometimes. Researchers collaborate across borders even when governments don't. Papers co-authored by scientists from rival nations are common. Data exchange happens informally through conferences and personal relationships. The scientific method, transparency, reproducibility, peer review, creates incentives for openness that counterbalance nationalist impulses. 3i Atlas might become a test case. Can the global astronomy community work together to study an interstellar object, or will competition and secrecy fragment the effort? The answer will shape not just our understanding of this comet, but our readiness for the next 100 interstellar visitors that are surely already on their way, unseen and unannounced, carrying their own mysteries across the light years to our doorstep. Part 13. Solar Storm and Space. Weather. Impacts beyond 3i Atlas. The solar storm barreling toward the inner solar system around November 22nd isn't just relevant to 3i Atlas. It's a reminder that space is not empty. The void between planets seethes with activity, charged particles streaming outward from the sun at hundreds of kilometers per second, magnetic field lines tangling and snapping, shock waves from coronal mass ejections propagating outward like ripples on a pond. This is space weather, and it affects everything from comets to spacecraft to Earth itself. Let's start with the Sun. Our star isn't static. Its surface roils with convection. Magnetic fields twist into loops and ropes, and periodically those fields snap, releasing enormous amounts of energy. Sometimes the energy manifests as solar flares, sudden brightenings in X-rays and UV that reach Earth in 8 minutes. Other times it drives coronal mass ejections, billion-ton bubbles of magnetized plasma hurled into space at speeds up to 2,000 kilometers per second. When a CME hits Earth, it compresses the magnetosphere, triggers geomagnetic storms, and creates auroras visible at mid-latitudes. For comets, a CME is a violent perturbation. The sudden increase in solar wind pressure compresses the coma and pushes the ion tail into new configurations. The magnetic field embedded in the CME can reconnect with the comet's induced magnetosphere. The magnetic structure created by the solar wind draping around the coma, generating acceleration regions and energizing particles. Some comets brighten dramatically during CME impacts as increased ionization pumps more energy into emission lines. Others show sudden disconnection events, where the entire ion tail detaches and drifts away, leaving the nucleus to grow a new one. 3i Atlas, if it experiences a CME around November 22nd, will undergo these effects. The plasma environment we've been hypothesizing about will be stressed, compressed, perhaps stripped away. If the plasma shield hypothesis holds, this is the moment of truth. A strong CME could blow away the shield entirely, exposing the nucleus and any jets or structures it's been hiding. Alternatively, the CME could thicken the shield, compressing the plasma into an even denser, more opaque layer. The outcome depends on details: the CME's magnetic field orientation, its speed and density, the comet's own magnetic structure, the outgassing rate. But space weather impacts more than comets. Spacecraft are vulnerable. High-energy particles accelerated by solar storms can damage electronics, corrupt memory, degrade solar panels. Astronauts outside Earth's protective magnetosphere face increased radiation exposure. Communication satellites experience disruptions as the ionosphere, buffeted by the storm, changes its density and refractive properties, bending radio signals unpredictably. GPS satellites, which rely on precise timing, can have their signals delayed by extra ionization, introducing positioning errors. On Earth, geomagnetic storms can induce currents in long conductors, power lines, pipelines, undersea cables. These geomagnetically induced currents can overload transformers and cause blackouts. The most famous example is the Carrington event of 1859, a massive solar storm that caused telegraph wires to spark and set fires. If a Carrington-class event hit today, with our dependence on electrical grids and electronics, the damage would be catastrophic: trillions of dollars, months of recovery. Modern forecasting aims to prevent this by predicting CME arrivals and allowing operators to take protective measures, shutting down transformers, reorienting satellites, warning airlines to avoid polar routes where radiation exposure peaks. The November 22nd storm, as currently forecast, isn't Carrington level. It's moderate, strong enough to generate auroras and minor satellite issues, but not catastrophic. Still, it's a reminder of our vulnerability. We live inside a star's atmosphere, essentially. The Sun's outer layers extend far, beyond its visible surface, and Earth orbits within that extended corona. We're protected by our magnetosphere, a magnetic bubble generated by Earth's molten iron core. But that protection isn't absolute. Particles sneak in near the poles, where field lines converge. Strong enough storms can compress the magnetosphere until its boundary, the magnetopause, gets pushed closer to Earth, exposing satellites to the direct solar wind. Mars, where MRO and Tianwen-1 observe ThreeI Atlas, lacks a global magnetic field. Its magnetosphere is induced, created by the interaction of the solar wind with the upper atmosphere, and localized crustal magnetic anomalies. This makes Mars more exposed to space weather than Earth. During solar storms, the Martian atmosphere experiences enhanced ionization and heating, and particles can precipitate deeper into the atmosphere. Spacecraft in Martian orbit must contend with increased radiation and atmospheric drag. MAVEN, one of the orbiters contributing UV data on ThreeI Atlas, is specifically designed to study how solar storms affect the Martian atmosphere. It's both observer and subject, watching the comet while experiencing the same space weather. This interconnectedness, the sun, the solar wind, planets, comets, spacecraft, all part of a coupled system, is the essence of heliophysics. You can't understand one component in isolation. A comet's behaviour depends on solar activity. A satellite's health depends on space weather. Earth's climate over long timescales is influenced by solar output. The November storm is a small thread in this vast tapestry, but by pulling on it we see how everything connects. For ThreeI Atlas specifically, the storm offers a natural experiment. Observers worldwide are poised to watch. If the comet brightens suddenly, if its tail morphology shifts, if previously hidden jets become visible, we'll have strong evidence that space weather and plasma dynamics play a major role in visibility. If nothing changes, we'll know the object is either intrinsically blurry or our observation windows are missing the interesting moments. Either way, we learn. But there's a logistical challenge: coordinating observations during the storm. Professional observatories have limited time allocations, often scheduled months in advance. Redirecting a telescope on short notice to capture a transient event isn't always possible. Amateur astronomers have more flexibility. They own their equipment and can observe whenever weather permits, but they're limited by daylight, clouds, and geographic location. Radio telescopes can observe through clouds and during daylight, but they need time to schedule and calibrate. The ideal scenario is a global network continuously monitoring ThreeI Atlas across all wavelengths before, during, and after the storm. Some efforts along these lines exist. Amateur networks coordinate through online platforms. Professional consortia share alerts, but coverage is patchy. What we might witness, if we're lucky and observant, is a comet caught in the act of transformation. The pre-storm baseline, whatever structure exists, however blurred. The storm impact, sudden changes, brightening, tail disruptions, plasma stripping. The post-storm recovery, a new equilibrium as the solar wind returns to normal and the comet rebuilds its coma. Documenting this sequence would be scientifically invaluable, a case study in space weather effects on cometary environments. And if the visibility paradox resolves during this sequence, if the blur clears and we finally see structure, it would vindicate the idea that plasma obscuration is real and dynamic, not just a convenient hypothesis. Beyond ThreeI Atlas, the storm reminds us that space exploration happens in a variable, sometimes hostile environment. We send robots to Mars, probes to the outer planets, telescopes to deep space, and we expect them to function reliably. But they're operating in a radiation-filled, magnetically active region, where conditions change hour by hour. Engineering for resilience requires understanding space weather, predicting it, and designing systems to survive it. The lessons learned from observing how this storm affects ThreeI Atlas, Mars orbiters, and Earth-based infrastructure will inform future missions. Interstellar probes, if we ever launch them, will spend decades travelling through the interstellar medium, a different regime entirely, but still governed by plasma physics and magnetic fields. The knowledge we gain here, in our solar system's backyard, scales outward. And there's something humbling about this. We build billion-dollar instruments, launch them into space, point them at distant objects, and sometimes the sun just throws a tantrum that disrupts everything. We're not in control. We're observers trying to make sense of phenomena that vastly exceed our influence. The best we can do is watch carefully, adapt quickly, and hope the universe cooperates long enough to reveal its secrets. 3i Atlas, hurtling through the solar wind wrapped in plasma, approached by a storm, is a microcosm of that larger struggle, the quest to see clearly in a universe that often prefers to remain obscure. Part 14. Interstellar Object Science. Post-3i Atlas Landscape. Step back for a moment and consider the sheer improbability of where we are. For all of human history until 2017, we'd never detected an object from another star system passing through our own. The galaxy contains trillions of rogue planets, comets, and asteroids drifting between the stars, ejected from their birth systems by gravitational interactions or stellar evolution. Theory predicted they should occasionally wander through our neighbourhood, but detecting them requires finding a faint, fast-moving dot among millions of background objects and recognising it as interstellar based on its hyperbolic orbit, a trajectory that doesn't, close into an ellipse but opens outward, implying the object came from outside and will eventually leave, never to return. Then came 1I/Oumuamua in October 2017. Discovered by the Pan-STARRS telescope in Hawaii, its name means scout, or messenger from afar arriving first in Hawaiian. The object was bizarre from the start. Highly elongated, tumbling, accelerating non-gravitationally in ways that couldn't be easily explained by outgassing because no coma was detected. It sparked intense debate. Was it a comet? An asteroid? Something else? By the time the scientific community mobilized for detailed observations, Oumuamua was already fading, speeding out of the solar system. We got tantalizing glimpses but no definitive answers. It left behind a mystery and a realization. Interstellar objects are real. They visit us, and we're unprepared to study them. 2 years later, 2I/Borisov arrived in August 2019. This one looked more like a traditional comet. Active coma, visible tail, composition rich in carbon monoxide. Multiple telescopes and even Hubble turned toward it, gathering more data than Oumuamua ever allowed. Borisov was a relief for some, proof that interstellar objects can be mundane, just comets from other star systems, nothing exotic. But even Borisov had oddities. Its carbon monoxide abundance was higher than typical solar system comets. Its nucleus fragmented during perihelion, and its trajectory offered clues about ejection mechanisms from distant planetary systems. Now, 3i Atlas, detected in April 2025, represents the third confirmed interstellar visitor. Each one teaches us something new. Oumuamua taught us they exist and can be weird. Borisov taught us they can resemble our own comets, but with chemical differences. 3i Atlas is teaching us about observation itself, how hard it is to see these objects clearly, how much we miss, how our instruments and methods might be inadequate. It's also the most thoroughly observed so far, with assets from Mars contributing data we couldn't get for the previous two. The detection rate is climbing. One interstellar object per 2 years might not sound like much, but consider that our detection capability is improving rapidly. The Vera Rubin Observatory, with its 8.4-metre mirror and massive field of view, will survey the entire visible sky every few nights once operational. Simulations predict it could find dozens to hundreds of interstellar objects per year. Some will be faint streaks barely distinguishable from asteroids. Others might be bright and active like Borisov, and a few might be as weird or weirder than Oumuamua, challenging our categories and assumptions. This creates a need for rapid response protocols. Interstellar objects move fast, typical velocities around 26 kilometers per second relative to the Sun. They're only observable for weeks to months before they fade beyond detection. Time, 0.5s, as Part 15, AI, Data Transparency and the Future of Space Science. Artificial intelligence enters this story the same way a quiet technician slips into a control room during a blackout, checking the cables, listening for the hum, trying to understand why the lights flicker. Artificial intelligence now sits behind almost every image we receive of comets, asteroids, and interstellar visitors, including the stubbornly mysterious object we call 3i Atlas. Artificial intelligence sorts the photons before we even know they exist, and artificial intelligence decides which faint patterns are real structure and which ones get thrown in the digital trash. You might not notice it at first, but once you see the role it plays, you can't unsee it. Artificial intelligence techniques such as image stacking start this transformation by taking hundreds or sometimes thousands of exposures from different telescopes and layering them together like translucent sheets on a light table. Artificial intelligence stabilizes them, aligns them, and smooths them until the noise fades and only the consistent details remain. Artificial intelligence excels at this because it is tireless, and because it never gets bored scanning through faint streaks of dust or jagged little lines that might be jets. Artificial intelligence also handles pattern recognition by learning the usual shapes comets make, such as curved tails, fan-shaped plumes, or symmetrical halos of gas. Artificial intelligence can spot a deviation from these templates long before the naked eye could, yet this same strength becomes a weakness when an object refuses to behave like anything in its training set. Artificial intelligence anomaly detection adds another layer to this story by scanning space images for outliers, those tiny details that drift outside the expected curve. Artificial intelligence flags sudden bright points or faint threads of emission. Artificial intelligence marks anything that looks statistically unusual. But here is the twist. If the system is trained mostly on typical comets, then anything too strange may be labelled as noise and quietly discarded. This becomes especially important when we talk about ThreeI Atlas, because amateur astronomers report geometric jets and something that looks like a ring, while official images smooth everything into a glowing blur. Artificial intelligence might be part of the reason these two worlds diverge. Artificial intelligence multi-wavelength fusion takes information from optical, infrared, and ultraviolet telescopes and pushes them together to create a single synthetic portrait. Artificial intelligence tries to resolve contradictions between wavelengths by averaging the differences or weighting the most reliable channels. This helps eliminate artifacts and sharpen true structure. But if an object is surrounded by a plasma environment that behaves differently across wavelengths, then artificial intelligence might treat genuine features as inconsistencies and flatten them out. The visibility paradox grows sharper when you realize that an automated system may be filtering the cosmos through our assumptions. Artificial intelligence also interacts with human observers in quieter, stranger ways. Online communities share raw images of ThreeI Atlas, some captured through small backyard telescopes and others stacked through clever Python scripts. People trade data files, swap calibration tips, and build homemade detection models. A person might post a raw exposure showing thin jets curling away from the nucleus, while an artificial intelligence pipeline trained to recognize only smooth cometary comas rejects it as a processing flaw. That single moment reveals a strange vulnerability. The human eye is sometimes more flexible than the algorithm, especially when reality refuses to behave. Artificial intelligence meets transparency issues right at this fault line. Space agencies such as NASA or the European Space Agency follow strict data release policies, often uploading raw files weeks after public presentations. These policies exist for good reasons, including verification, calibration, and scientific review. But the delay creates suspicion in an era where amateurs post their own observations instantly. Artificial intelligence is already integrated into some agency pipelines, and those automated steps are not always described in detail. People wonder whether subtle processing choices, smoothing filters, or artifact cleaning algorithms might hide important features simply because they fall outside what the system expects to find. This does not imply deception. It implies a structural blind spot. Artificial intelligence prompts an uncomfortable speculation here. Perhaps the thing hiding the structure of ThreeI Atlas is not a physical plasma shield but a procedural one. Artificial intelligence filters, human calibration decisions, smoothing rules, wavelength weighting, and image stacking assumptions might create a kind of digital cloak. If an interstellar object behaves in a way no comet ever has, then tools trained on normal comets would erase the very details we need to understand it. The visibility paradox could emerge from software pipelines just as easily as from a sheath of charged particles. Artificial intelligence becomes even more important when we look toward future interstellar visitors. More will arrive, and some will be fast, strange, or wrapped in unfamiliar chemistry. Telescopes built for the solar system were not designed for objects that come screaming in from other stars with surfaces baked by cosmic rays and cores frozen before our sun existed. Artificial intelligence systems must be retrained to accept the possibility of weirdness rather than averaging it away. As more interstellar travelers appear, scientists will need hybrid approaches that combine classical physics, flexible artificial intelligence models, and open data ecosystems where Amateurs and professionals collaborate. Artificial intelligence also forces a philosophical question to the surface. People have always asked whether we are looking hard enough at the universe. Artificial intelligence allows us to look more widely and more quickly, but it also encourages us to rely on templates, patterns, and familiar shapes. If an alien artifact drifted through our skies tomorrow, would our systems classify it as debris because its structure does not match a comet profile? Would our algorithms smooth out its angles, its reflections, its strange behaviours? We might miss the extraordinary simply because our tools are optimized for the ordinary. Artificial intelligence gives us a story worth remembering, told through a simple micro moment that echoes everywhere. An amateur astronomer might upload a quiet frame captured from a driveway on a cold night. A thin jet barely appears on the edge of the nucleus. The system trained to clean noise studies the pixel, compares it to its models, and decides it must be a smudge. It discards it with a soft click, leaving only a sterile blur. That faint streak might have been a clue to something we have never seen before. Artificial intelligence leads us to a question that stays with you after the screen goes dark. In a universe full of strangers, how much of their story do we miss simply because we were not built to see them?